Today we are going to learn about rational numbers and irrational numbers. So we have to figure out what the difference is between the two. What's a rational number and what's an irrational number? Let's start with the numbers you're used to seeing, and those numbers are rational. So what makes up rational numbers? Whole numbers are all rational. Remember that whole numbers start from 0 and they keep going up on the number line. 0, 1, 2, 3, 4. They're not decimals, not fractions, just whole numbers. So those all belong to the rational number family. But rational numbers, they're more than just whole numbers. If you include the negative versions, so negative 2, negative 1, 0, 1, 2, those are all technically rational as well. Okay, so these are all numbers that aren't decimals and fractions. Well, what about decimals and fractions? Let's look at fractions first. Fractions are rational numbers as long as you can express them using integers. If you notice right here, these are all integers. 1, 2, 7, negative 3. Those are all integers. Your denominators here are all integers. 2, 5, 9, 11. Those are all integers. What about something that looks like this, though? Because this is a tricky one. What about something like 2.5, right, over, let's say, 2. 2.5 is not an integer. Is this technically a rational number? Well, remember that we can actually change this fraction. Let's multiply both of these by 2. If I multiply my numerator by 2, I end up with 5. I multiply my denominator by 2, I end up with 4. So these fractions are equivalent to each other. 2.5 halves is the same as 5 fourths. Because these are equivalent, look at this. This version of the fraction, that is an integer, that is an integer. So this is rational, which means that this right here is rational as well. So generally speaking, as long as it's a decimal that we can turn into an integer, um, decimals and fractions will end up being rational numbers as well. Now, decimals just by themselves, as long as they either terminate or repeat, they will be rational. Here we have an example of a decimal that terminates, 2.5, the decimal ends. Here we have an example of a decimal that repeats. This 6 right here will repeat forever, but as long as it's repeating a sequence, it's still considered rational. Right here we have a negative zero point 0.3. It's still a decimal that terminates, therefore it's still a rational number. So we have covered the bases of all rational number groups. Now, what do these all have in common? What's the definition of a rational number? How do we get that word rational from all those sorts of numbers? Do you see a word in this rational that we've looked at in class before that might look familiar as a math concept? We actually spent an entire unit on that. That word that's kind of hidden inside the word rational is ratio. Remember, we can actually write a ratio as a fraction. So here we go. 2/3 is a ratio. It's a 2 to 3 ratio. This is where the word rational comes from. That 2 and that 3. A rational number is technically any number that can be written as a ratio of two integers. Now, for us, what that looks like more than anything else is any number that you can write as a fraction is a rational number. So let's take a look at 2.5. Can you write that as a fraction? Absolutely. 5 halves is 2.5. 5 halves is a ratio, therefore this is a rational number. 6.6, repeating forever. Can I write that as a ratio? I absolutely can. How about 20 over 3? Will that equal 6.6 repeating? It absolutely will. Therefore, because I can make a ratio that equals this, it'll end up being a rational number. Negative 0.3, oh yeah. Negative 3 tenths, that's a ratio. Oh yeah, okay. That's a ratio. Therefore, that negative zero point 0.3 is a rational number. So, as long as I can make a ratio, a fraction, that equals any of the numbers I'm trying to find, it'll end up being a rational number. So what does that leave left? Because that seems like that's pretty much every single number that we've dealt with before. What else is there that's left over? What would technically be an irrational number? Well, if a rational number is a number that can be written as a ratio, An irrational number is a number which cannot be written as a ratio of two integers. What does that number look like? Let's start off in decimal form. In decimal form, we have a special property with irrational numbers. They do not repeat or terminate. That means that a decimal that's an irrational number will go on forever. It'll never stop, but it never repeats the same sequence of numbers, ever. Here's an example. You can make them up pretty easily. I put 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and this would keep going on like this forever. So it would be 17, 18, 19, 20, 21 at the end of it. This is a decimal that will never end. As long as I keep adding numbers to it, it'll never end. And as long as I keep adding the next number onto it, there's never a sequence that's going to be repeated. I mean, you'll get a 1 here, and then you'll get a couple ones here, and a 1 here, and a 1 here, and a 1 here, but it's never the same sequence. Notice, it's always going to be changing. This whole thing would end up being an irrational number. All the numbers next to each other in a decimal form will end up being an irrational number. Let's make another one. 12,346.10, 100, 1000, 10000, and so on and so forth. That is a number that's never going to end as long as we keep adding those powers of 10 onto them. And it never repeats the same sequence. It's repeating ones and zeros, but this is a 10. This is 100. This is 1,000. This is 10,000. This would be 100,000. Next would be a million. It's never repeating the same sequence of ones and zeros. It's always changing. So this whole thing right here, as long as I kept going on with it, would end up being an irrational number. Alright, so we've learned how to make up our own decimals that don't end and don't repeat sequences. But where do we see irrational numbers? Where do they come from? Well, let's start by looking at places where they don't come from, and then we'll end up deriving where they do. Okay? So, we're going to take a look at something that you've learned in the past, perfect squares, and what happens when you take the square root of them. So 4 is a perfect square. We know that because if we take the square root of it, we end up getting 2. A nice whole number, no issues. 9 is a perfect square because if you take the square root of it, you end up with 3. Again, a nice whole number, no issues there. So, it's safe to say that because 4 is a perfect square and 9 is a perfect square, when you take the square root of them, you'll end up with nice whole numbers. Now, what happens when you get a number in between the square root of 4 and the square root of 9? It has to end up being a number somewhere between 2 and 3, but what number is it? Let's look at an example. Let's say the square root of 6. It's in between the square root of 4 and square root of 9. Therefore, this is going to be somewhere in between 2 and 3, but what is that number? Is it going to be a decimal? Is it going to repeat? Is it going to terminate? Well, nope. It's going to end up being some crazy number like 2.4494897, and there's going to be more numbers, and it actually goes on forever. But the weird thing about this is it will never repeat the same sequence of numbers. It is a decimal that just has no end to it, and there's no pattern to it whatsoever. It's just going to keep on going. That's where That's one of the places where irrational numbers come from. When you take a number like 6, 6 is not a perfect square. When you take the square root of it, that square root ends up being an irrational number. This is an irrational number. 6 is not. 6 is an integer. It's a whole number. 6 is not an irrational number. But when you take its square root, oh boy, you end up with quite a decimal. So this whole thing, the square root of 6, is an irrational number. Basically a law. The square root of any whole number that isn't a perfect square is irrational. So take any number that you know is not a perfect square. Do you remember examples of what perfect squares are? Because then it'll be easier to take one that's not. Okay, 1's a perfect square because 1 squared is 1. 2's a perfect square. Nope, hold on. That's not true. 2 is not a perfect square. However, 4 is a perfect square because 2 squared equals 4. So we, didn't get that pen. Get that pen. 4 is a perfect square. 9 is a perfect square. 16 is a perfect square. Separate these with commas so you can tell the difference between the numbers. Okay. 25 is a perfect square. 36 is a perfect square. What's next? Think about it. What's next? Did you get 49? Yeah, you should have. Okay, 49 is a perfect square. And we can keep going on and naming all the perfect squares. This is 1 square, this is 1 squared, this is 2 squared, this is 3 squared, this is 4 squared, 5 squared, 6 squared, 7 squared. We can keep listing all the perfect squares. So if you take the square root of any number in between here, it'll end up being irrational. So here's just some that I picked. Square root of 14 will end up being some crazy decimal that doesn't end and it doesn't repeat. Square root of 26 is going to be some crazy decimal, doesn't end, doesn't repeat. Square root of 2. Even a nice small number like 2 will end up, if you take the square root of it, will end up being some irrational number because it's in between the square root of 1, which is 1, and the square root of 4, which is 2. So because it's in between those perfect squares, it's going to end up being some crazy, it's 1 point, some number that is ugly and it doesn't end and it doesn't ever repeat a sequence of numbers. So your irrational numbers are numbers that are either, you can define them as square roots of not perfect squares, or decimals that don't ever end and they don't ever repeat sequences. Whereas rational numbers that are either fractions that use integers or decimals that either end or repeat sequences for the rest of their existence. And that is the difference between rational numbers and irrational numbers and